I'm so let's welcome Philippe Biane from Paris Est, who is going to talk about non-crossing partitions, interval partitions, and the Bruhat order, take 2. And I'm going to start the recording.
Okay, thank you very much. So thanks again for the invitation. And again, I'm sorry for the people who were here there on Friday and when I had a very bad connection. I hope this goes much better today. Apparently, it's stable now. My talk will be about some combinatorial structures which have been very much studied, non-crossing partitions, intervals partitions, and I want to put them into some perspective coming from geometry, from Coxeter group theory, more precisely. So non-crossing partition, in short, you can see one non-crossing partition here on the top here. So you have points and you draw points using semicircles or things which look like semicircles when they are in the same part. You see that here you can draw the semicircles so that they don't cross. So it's called non-crossing partition. I will give a more formal definition just after. And below is an interval partition. So where the parts of the partition you see are intervals. They consist of consecutive points. So let me now be more precise. I consider set partitions of the set of integers from 1 to n. And I say it is non-crossing if there are no crossing. So a crossing, what it is a quadruple of points, a, j, k, l, which are in this order, and such that a and k are in the same part, j and l are in the same part, but the two parts are distinct. So here is what happens in this case. So you have h here, j, k, l in this order. So j and l are in the same part, k and I are in the same part. And you see that when you draw semicircles joining them, they have to cross at some point. So this is what you want to avoid. And a set partition is called non-crossing if when you draw when you join the consecutive points in a part, there is no such crossing. Here is an example. This partition of numbers from 1 to 8. And it is very convenient to draw such partitions on a circle. When you draw them on a circle, so you have points like 2, 3, and 7, which are parts with only 1 point. And when you have a part with 2 points like 6 and 8, you can draw an edge between 6 and 8. And when you have a larger part like this one with 4 elements, you can draw edges between consecutive points. So here you get a triangle. And the point is that all these do not cross. I mean, all these edges do not cross except maybe at the boundaries. Okay, so this is non-crossing partition. Some basic facts now. Non-crossing partitions, they form a lattice for the order, which is the inverse of the refinement order. And the number of non-crossing partitions is well known to be the Catalan number, which is, well, one of the most famous numbers in combinatorics. So there have been many, many papers on these structures. In the first one, which I think is the one by Creveras in 1972. And it's now one of the most popular, I would say, combinatorial structures to be studied in combinatorial literature. My main source of interest in this object comes from the theory of non-crossing cumulants, which was developed by Schascher in the beginning of the 90s. So what are non-crossing cumulants? In order to define non-crossing cumulants, we start with an algebra, A, which in general will be a non-commutative algebra, in general over complex numbers. You could consider other fields, but I mean, usually we consider them over complex numbers because we want to make some probability theory out of that. And tau is a linear form on A. And then one defines multilinear functionals, Rn, by this formula, which is an implicit formula. So the formula is the following. So we have tau of A1, AN, which is a sum over all non-crossing partitions. This is where the non-crossing partition appear. All non-crossing partition of n, of some product, R pi of A1, AN. So the product is defined in the following way. This is a product over all the parts of the partition pi. And for each part P of the partition pi. Let me call it I1, IP. So this is a part of the partition. I evaluate this multilinear functional. Here, this is just the size of the part of P. And I evaluate it on the elements I1, IP, that is here on AI1, etc., AIP. Okay, so this is a definition which is indirect. And let me see in example what it gives. So the first is R1. So the first one is just tau, because when I do my formula, I just see that there is only one partition of the set 1. So I just give this identity. So this gives me that R1 is equal to tau. And now for the second, I evaluate tau of A1, A2, and this is R2 of A1, A2, corresponding to this non-crossing partition, 1, 2, plus R1 of A1, R1 of A2, corresponding to the partition with 2 parts. And I can solve this because I know already R1, so I can find R2. And I see that R2 is just tau of A1, A2 minus tau of A1, tau of A2. In some sense, it is a covariance. If you think of tau as a kind of expectation, if you think in probabilistic terms, R2 is just the covariance. And now there are more complicated formulas. For example, if you go to 3, then you see that tau of A1, A2, A3 is equal to R3, evaluated on A1, A2, A3, corresponding to the only partition which has only one part. And then you have a sum of terms. And now you can invert this formula because all the other terms involve only things that you already know, like R1 or R2. And you get this formula, which is here, which gives you the third non-crossing cumulant as a multilinear functional of A1, A2, A3 on your algebra.
Sorry,
general,
so
sorry, yes?
The variables are always substituted in increasing order, right?
Yes, yes. You always have to use increasing order. The order is important because I don't assume that my algebra is commutative. So the order in which you take the product, so for example, this product here, you cannot exchange the order of the product.
Thank you.
It's very important each time that you take the increasing order. Okay, so here you have A1, A2, A1, A3, it's always in increasing order. Okay, and now in general, I gave you the formula for the first ones, but in general, there is an inversion formula that you can find. It is given by a sum. So Rn of A1, An is given by a sum. There is some function mu, which is the Möbius function on the set of non-crossing partition, and tau pi of A1, An, which is given by a similar formula as the definition I gave for R. So if you go back here, you see this formula here. You see that you have a formula over non-crossing partitions of A1, A2, A3, and tau evaluated on this non-crossing partition. You can easily understand what it means on this formula. And there is such a general formula in the general case, which was found by Speicher. Now, what Speicher did is he used the vanishing of the non-crossing cumulants to define the notion of free independence. I mean, the notion of free independence had been already defined by Voculescu, but Speicher found an alternative definition using these free cumulants. I will not go into this definition because it's not here. I'm more interested in hearing combinatorics and geometry, but I want to motivate the study of these objects. And well, the basic remark is that the remark from which Speicher started is that if you do the construction that I did, but using a commutative algebra and using the lattice of all set partitions instead of the lattice of non-crossing partitions, then you obtain formulas, cumulants, which were found by Rota in his approach to the independence in classical probability. So what Speicher did is that he observed that if you replace the lattice of all non-crossing partition by the lattice of non-crossing partition, then you get a very similar theory to the theory of Rota of independence in classical probability, and it explains, in some sense, the free independence. So it gives a combinatorial insight into the free independence of the Euclid. Well, now let's go to interval partitions. So a set partition of the set 1n is an interval partition if its parts are just intervals in the usual sense in the set of integers. So an interval partition is determined by the first member of each of its parts. It's easy to see. So it follows that the set of interval partition, it forms a Boolean lattice. If we look at the refinement order, it is a Boolean lattice. Its order is 2 to the n-1. And it is also a sublattice of the set of non-crossing partition, because it is also easy to see that an interval partition is always a non-crossing partition. So after Speicher introduced non-crossing cumulant, he had the idea of looking at the set of interval partition, and he introduced Boolean cumulants with Vorudi in 1997 by a very similar formula. So the formula is, again, implicit formula, where tau of A1AN is evaluated as the sum of the whole interval partition of some cumulants, B pi. So B pi here are given by a family Bn of multilinear functional on your algebra. So we are again have an algebra A with some linear form tau, and the cumulants, the Boolean cumulants, are given by this formula, and with a very analogous computation as what I did in the case of free cumulants, it is easy to see that there is an inversion formula, that the free cumulants, the Boolean cumulants can be expressed in terms of the moments of the products, tau here, of the A1AN, by some inversion formula where mu is the Möbius function on the lattice of interval partitions. And again, one can use these Boolean cumulants to define a notion of Boolean independence. That's what Speicher and Vorudi did in their paper. So these two notions, the notion of interval partition and the notion of non-crossing partition, give rise to some probabilistic application in non-commutative probability. And basically, the story stops here because Speicher has shown that essentially the classical independence, the free independence that I obtain using free cumulants, and the Boolean independence obtained using Boolean interval partitions, they are essentially the only general notion of probabilistic independence in algebras which satisfies some natural requirements. Well, of course, you could loosen the hypothesis, and there are some other like monotone independence which you can get. But essentially, if you put some axiometric framework, Speicher has shown that essentially you have only three possible independence theories. So this is my starting point for looking at these objects, that in some sense they are characterized in a probabilistic way. And what I want to show is that these combinatorial structures, well, not so much the classical set partitions, but at least the non-crossing and the interval partitions, they are very deeply related to the theory of Coxeter groups. And so this is the aim of this talk, is to explain this and to show that one can generalize these objects to very general finite Coxeter groups. And they have some very deep properties which are not so much apparent when you look at them at first sight. So let me summarize what I've done. So I talked about non-crossing partitions. So you see an example here of a non-crossing partition, interval partitions. And I observed that the interval partitions form a Boolean sublattice of the lattice of non-crossing partitions with respect to the same order, the inverse of the refinement order. So now, how do we go to Coxeter groups? Well, the first thing that we have to to observe is that one can embed the set of non-crossing partitions inside the symmetric group. So this is a basic fact. So how do we do that? Suppose you have a non-crossing partition like I draw here. Well, what you do is you take the parts of the partitions and you consider the parts of this partition as the cycles of a permutation. So here I have three parts which consist of 1 point, so they correspond to 3 fixed points of the permutation. There is one part which has 2 elements, so it corresponds to a cycle for the 3 or for the 2, sorry, in the permutation. And I have a cycle for the 3, 1, 4, 5, and I am careful that I take the order, the cycle in this order. So the cycle is in the same order as the cyclic order around the cycle that I have here. So if you do that, you get a canonical way of embedding the non-crossing partitions inside the symmetric group. It's easy to see that if you have a non-crossing partition, you get a permutation. And conversely, there is a certain subset of the set of permutation that come from non-crossing partitions. Okay. And of course, since interval partitions are also non-crossing partitions, you can do the same with interval partition. It's just a subset. Okay. So here is a picture of the lattice of non-crossing partitions, NC of 3. So this is a lattice of non-crossing partition on the set of 3 elements, and as embedded in the symmetric group S3. So here we have the identity corresponding to the partition with 3 parts. Here we have 3 partitions with 2 parts. So these are all transpositions. They correspond to transposition when I embed in the symmetric group. And here I have the cycle for the 3, 1, 2, 3. And in red, I draw the interval partitions. And as you see, so this is the order relation here. You see the Hasse diagram of the order relation. And you see that the red part is a Boolean lattice. Okay, it's a square here. It's a square lattice. Okay, so slightly more complicated picture. We have the okay. So I'm afraid you cannot see here the top of the. I'm not sure you can see the top of the picture, but here
I see it.
You can see it. So it's because I cannot see it because I have some little. Okay, but so here you have just the identity. Here you have all the transpositions in the symmetric group, and then here you have some non-crossing partitions and the images inside the symmetric group, and here you have the 4 cycle 1, 2, 3, 4. And you see this is the lattice of non-crossing partition, and in red you see the lattice of interval partition. And you see that as a lattice it forms a Boolean lattice. You see it's a cube essentially, and the number, it is ranked, and the number of elements in the rank are 1, 3, 3, 1. So the binomial coefficients. Okay, so in this way, you see that you can embed symmetric, non-crossing partition and interval partition inside the symmetric group. Also, now the question is, can we do this in some, is there some intrinsic characterization? Well, so the main message, I would say, of my talk of today is the following. The non-crossing and the interval partitions are very much related to some order relations, 2 order relations on the symmetric groups. So let me describe this. Let's see the full cycle, 1, 2, 3, etc. n. So the cyclic permutation, which permit 1, 2, 3, n in this order. My claim is that the non-crossing partitions are the permutations sigma, such that sigma is smaller than c in the absolute order. That I'm going to define the absolute order now. But so NC of n can be realized as a set of non-crossing partitions which are smaller than c in the absolute order. And moreover, this order coincides with the natural order on the set of non-crossing partitions. So the inverse refinement order. And there is a similar definition, a similar characterization. Interval partitions are the permutation sigma, such that sigma are smaller than C with respect to the Bruhat or strong order. So I of n is a set of sigma, which are smaller than C with respect to Bruhat order. And again, the order for which it is a Boolean lattice corresponds to the Bruhat order. So of course, I need to define what are the absolute order and the Bruhat order. And these things actually can be defined for any finite Coxeter groups. And even not only finite actually, but I will be only interested in finite Coxeter groups here. So my task now will be to define what are Coxeter groups, what are these two relations on a Coxeter group, and what properties of this object are there. And we'll see that there are some quite amazing and deep properties of this object. I will give you a glimpse into that, I hope, in the rest of the talk. So first, we need to go to finite Coxeter groups. So what are finite Coxeter groups? So let's take V to be a finite dimensional Euclidean space, and O of V to be the orthogonal group of V. So the linear transformation which preserves the Euclidean structure. So a Coxeter group, or finite Coxeter group, will be a finite subgroup of the orthogonal group, which is generated by orthogonal reflections. So it is just a definition, or reflection group. And let T be a subset, the subset of all the reflection in my group. So as I said, this is a generating set of, it is a definition of the Coxeter group. Then a reflection T in this set T is given by some formula like that. T of V is V minus, so there is some vector alpha, which is the direction of the reflection. And the orthogonal of alpha is a hyperplane. It is the hyperplane of fixed point of the reflection. So T of V is V minus alpha dot product with V times alpha. And here, alpha and of course, you see in this formula, you could use either alpha or minus alpha, it gives the same formula. So the vectors alpha or minus alpha, which occur in these formulas when T is a reflection, they are said to be the set of roots of the vector of the group W. So it is a finite set of vectors in W, and it has to satisfy some relation in order that the reflection associated to these roots form a Coxeter group. Okay. Inside the T, there is a subset of reflection which plays a very special role. And in order to define it, I need to find a fundamental domain for the action of W. So W is a finite group of orthogonal reflection. It turns out that I can find a cone which is bounded by a finite number of hyperplanes, and such that this cone is a fundamental domain for the action of W. That is, every point is corresponds through the action of W to a unique point in this cone. So the hyperplane which bounds this fundamental domain, they form what is called a simple system of generators. I will give you the very explicit example in this case of the symmetric group if you are not familiar with that very soon. So the set of roots corresponds to two subset of roots. One set which is called the set of positive roots, the one which have a positive inner product with the fundamental domain, and the negative of this set of roots, the one which have a negative inner product with respect to the fundamental domain. And there is a set of, inside the set of roots, there is a positive roots corresponding to the simple reflection, since S is a subset of T. So let me be more specific now and give you the example of the symmetric group. The symmetric group acts on the Euclidean space V, which is the hyperplane sigma of xi is equal to 0 in the Euclidean space Rn with n coordinates, n real coordinates. It acts just by permuting the coordinates. It's easy to see that this equation is invariant under permutation of the coordinates. So the reflections here, in this case, are just the transpositions. Well, we all know that the transpositions that generate the symmetric group. The simple transpositions, the simple reflections are just the reflections I plus 1. The roots are the vectors ei minus aj for e smaller than j, so the positive roots. And the simple positive roots are the ei minus ei plus 1. Okay. So this corresponds to these correspond to these. And you see the hyperplane defined by the orthogonal of a root, ei minus ej, is the upper plane of equation xi equal to xj. And you see that it is preserved by the transposition of the two coordinates, xi and xj. Here is a picture in the case of S3. So S3 acts on the hyperplane, x1 plus x2 plus x3 equal to 0. And inside this hyperplane, I have a cone given by the inequalities x1 bigger than x2 bigger than x3. This is the cone which is here, that you can see, bounded by these two hyperplanes. There are three reflections in S3. The three reflections are the reflection with respect to the three lines which are here. Okay, two of these lines are the simple correspond to the simple reflections, to the x1 and x equal x2 hyperplane, and x2 equal x3 hyperplane. And there is a third hyperplane which corresponds to x1 x equal x3. So you have two simple roots which are orthogonal to the hyperplanes which bound the cone, which are here in blue. You have negative roots in green, and there is one root which is positive, and it's not simple root, corresponding to the orthogonal of this hyperplane, and it corresponds to the reflection 1, 3, the transposition 1, 3, which is not a simple transposition. It's the only transposition in S3 which is not a simple transposition. Okay, so I hope you, if you have never seen a Coxeter group before, this maybe gives you a hint at what this structure looks like. So of course, in the general case, it's much more complicated, but at least there is a complete classification of all finite Coxeter groups. And these things are well known. I mean, these can be classified using Dimikin diagrams and Coxeter diagrams, things like that. So, but I will not go into that. Okay, so I need now to introduce another notion, which is that of Coxeter element. So in a Coxeter group, a Coxeter element is just a product of all the simple generators in the group in some order. So if you want, C is SI1, SI2, SIN, where the S are all the simple reflection in some order. I mean, you can choose the order that you want. And the great insight of Coxeter is that he saw that he introduced these elements and saw that they are all conjugate in the group W, which is a non-trivial fact, of course. And well, in the case of the symmetric group, the Coxeter elements, they are all cycles of maximal length. But all the Coxeter elements are cycles of maximal length. But I mean, if you have chosen the simple roots, the simple generators, then you don't get all cycles of maximal length. I mean, some cycles of maximal length do not occur as Coxeter elements. Okay, so now I can define the absolute length and the absolute order on a Coxeter group. For this, I consider T the set of all reflections. In the case of the symmetric group, it is the set of all transposition. This is a generating system for the group W. Because it is a generating system, there is a length function associated to W. So this length function, LT of V, this is by definition the minimal number of reflections that you need in a decomposition of V as a product of reflections. So if you provide V is T1, T2, Tk, with K a minimal possible number, then K is the length of V. with respect to T. It turns out that one can give a general formula in the case of Coxeter groups, and for T is a generating system. LT of V is equal to the codimension of the set of fixed point of V. The set of fixed point of V is, so it's a hyperplane. It's not a hyperplane, a subspace in the space V. It's a set of fixed point of some orthogonal transformation. So it has a certain codimension, and this codimension turns out to be the dimension, the length. For example, if V is a reflection, then its length, of course, is 1, because it is written as a product of one reflection. And the codimension is the dimension of the fixed point of the reflection, so it's a hyperplane. In the case of the symmetric group, there is a simple formula. The length of a permutation is n minus the number of cycles of the permutation. Okay. Now, using this absolute length, I can define the absolute order of the symmetric group, on the Coxeter group. So in order to define this absolute order, I will define the cover relation for this order. For this, I look at pairs, V and W of elements, which differ by some reflection. That is, I suppose that V times W minus 1 is a reflection. Then I said that V is smaller than W if and only if the length of V is smaller than the length of W. And of course, if the length of W is smaller than the length of V, I would have the opposite inequality. So this means that every pair V and W which differ by some reflection, they can always be compared. One of them is always larger than the other for this order. And you can complete this order by transitivity. It turns out that this really defines an order relation on the group W. Well, using this definition, it's not so easy to understand what this order is. So there is a better way of understanding this order, which is the following. We can characterize this order using the triangle inequality in the following way. So in general, V and W satisfy V is smaller than W if and only if we have the following equality. The equality says that the length of W is the length of V plus the length of V minus 1 W. In general, if you take arbitrary V and W, the left-hand side of this equality will always be larger than the right-hand side. This is a triangle inequality in the group W with respect to the length function LT. But if we have equality here in this triangle inequality, then we say that V is smaller than W with respect to the absolute order. It's another way of defining the absolute order. And one can check that these two ways of defining the order are equivalent. They both define an order relation. So a geometric way of explaining this is to say that V is smaller than W if V is on a geodesic from the identity to W in the Cayley graph of W, where the Cayley graph is taken with respect to the set of reflections which are here. So there is a structure of Cayley graph on W where the edges are given by pairs VW such that VW minus 1 is a reflection. And when you look at this graph, you have a notion of distance on the Cayley graph, a notion of geodesic, a minimal path of minimal length between 2 points. And so V is smaller than W if V lies on a geodesic between E and W in this Cayley graph. Now I define parallel to the absolute length, I define the Bruhat length. So instead of a T, I look now at a S, the simple reflections. S is a generating system for W, and I call LB the associated length function on W. So by definition, LB is the minimal number of simple reflections that you can use in a decomposition of V as a product of simple reflections. Okay, so K is the smallest number that you need in order to write V as a product like that. One can prove that in a general Coxeter group, the length is equal to the number of inversions of V. that is a number of reflections, V, such that the length of Vt is smaller than the length of V. These are called these T are called the inversions of V, and one can prove this formula in general in a Coxeter group. And in the case of the symmetric group, we have the usual formula for the number of inversions. The number of inversions is just a number of I smaller than j, such that sigma I is strictly bigger than sigma of j. So corresponding to the usual notion of number of inversions in the symmetric group. And now the Bruhat order. Again, I look at two elements, V and W, in my group, which differ by some transposition or some reflections, say. Then I will say that V is smaller than W with respect to the Bruhat order if now the Bruhat length is smaller than the of V is smaller than the Bruhat length of W. And again, we can use this relation by transitivity, we can extend it to an order relation on W, which is called the Bruhat order or the strong order on the Coxeter group W. Again, there is another characterization which is more convenient than this one, which is by this characterizes only the cover relation in the Bruhat order. But if we want to compare two elements which are quite far, we have a more convenient realization of this order, which is the following. So V is smaller than B. If and only if V has some reduced decomposition, such that it is a subword of a reduced decomposition of the larger element, W. So W can be written S1 Sk, a decomposition of smallest possible length with elements in S. And V can be written as a subword Si1 Sij, which is also a reduced decomposition in a decomposition of minimal length. Okay. So this gives you, in some sense, this is a kind of subword of order in the Coxeter group. Well, now I can define non-crossing and interval partitions for general Coxeter groups. So let me take C, a Coxeter element. So let me recall that a Coxeter element is a product of all the simple reflections. And I will call NC of WC the set of all elements which are smaller than C with respect to the absolute order. It turns out that this NC of WC is a lattice for the absolute order. So this is a result of basis and Brady and Watt in the general case of Coxeter groups. It's a non-trivial result. I mean, it uses really some non-trivial theory of Coxeter groups. And what we define with Matthieu is the following other lattice, which is a set of all what we call the set of interval partition with respect to W and C, which is a set of all W in W, which are smaller than C, but with respect to the Bruhat order. Okay, and it turns out that this set is a sublattice of NC of WC with respect to this order, and it is also a Boolean lattice with respect to this order. It turns out that these two orders coincide on this set, and it is a Boolean lattice whose order is equal to 2 to the number of elements in S. So the number of simple generators of the Coxeter group. Actually, if C is written as the product S1 Sn of simple reflection, then so all S1 Sn are distinct simple reflections, then V is an interval partition, so it belongs to this interval if and only if it is a product Si1 Sik with I1 smaller than I2 smaller than K. And it is easy to see that this implies immediately that this is a Boolean lattice. Actually, it is isomorphic to the lattice of all subsets of the simple roots, as you can see in this way. Okay. So here is the again the picture of the lattice of non-crossing partition in S4. So here we have the Coxeter element 1, 2, 3, 4, And here we have the lattice of all non-crossing partitions, and the lattice the lattice of all non-crossing partition here. And in red, we have the lattice of interval partitions. And now I show you what happens if you change the Coxeter element. Sorry, I will show you later. Sorry. If you change the Coxeter element, actually you get, since all Coxeter elements are conjugate, you will get the same, not the same non-crossing lattice, but an isomorphic non-crossing lattice, and also an isomorphic interval partition lattice. But the way they are embedded inside the other is more subtle than that. We will see it later. Okay, so what we see here is that here we have some instances where the Bruhat order and the non-crossing, the absolute order coincide. All these red edges here are places where we have the same order here. But there are some places here where the Bruhat order and the absolute order do not coincide. And we are going to try to understand this, and this is where it starts becoming more subtle, and some really nice things happen in the theory of Coxeter groups. So in order to do that, we will introduce two order relations. So one order that I will call the square order, and one order that I call the double order. So if V and W are in a cover relation, that is, V is smaller than W, and the difference, so VW minus 1, is a reflection. Then two things can happen. Either V is smaller than W with respect to the Bruhat order, or V is bigger than W with respect to the Bruhat order. The two things can happen, and actually the two things happen in general in Coxeter groups. And what we do is that we put V is smaller than W for the square order if we have both this order relations, and V is smaller than W with respect to the double order if V is smaller than W, again, for the absolute order. This is something we have assumed, but now V is bigger than W with respect to the Bruhat order. So in some sense, this corresponds to the case where the two orders coincide, the two cover relations. This cover relation is also an order relation for the Bruhat order, but here, this cover relation is not a relation, it's an opposite relation for the Bruhat order. One can complete this by transitivity, and then one gets two order relations on W, which I call the square order and the double order. And now we are going to see that this satisfies some subtle relation when you look at these orders on the space, on the lattice of non-crossing partitions. So let me give you examples. So first, in the case of S3, or the non-crossing partition of order 3, so we have here in black, I put the square order, and in red, I put the double order. Okay, so you see that all the relations are square relation except this one, which is a double relation. This means that here, the absolute order and the Bruhat order coincide on these pairs of elements, but here, 1, 3, actually 1, 3 is the largest element for the Bruhat order in the Coxeter group in S3. So N1, 3 is bigger than this one. It's larger than this one in the Bruhat order. So you see that here, there is some distinction inside this, okay? Here is a picture of what happens when you look at the set of non-crossing partitions that I showed before. So in black, I have put all the square relations, square order relations, and in red, all the double order relations. So this means that on all these pairs, the absolute order and the Bruhat order coincide. I mean that these relations are order relation for the absolute order and for the Bruhat order. But this relation, for example, is a relation. This one is smaller than this one for the absolute order, but it is the opposite. This one is larger than this one for the Bruhat order. Okay, so we have opposite order relations in the case of these double relation, red relations. So you look at this picture, and it shows you what happens when you take this Coxeter element, 1, 2, 3, 4. But now, if I change the Coxeter element, then it turns out that the picture is not isomorphic to the preceding. As you can see, for example, if you look back, at this point, there was some relation here, but this relation here is somehow missing. And you can check that these two orders, if you look at both of them simultaneously, they form a different picture from the one before. So something is happening here. Okay, so my next task will be to explain how these relations can be characterized directly, because I characterized here the relation for the square order and the double order only in terms of the cover relations. But I want to give a more, I would say, a better characterization of this order. For this, I need to introduce what I call parabolic subgroups. So suppose I have, sorry, this should be a W. So W, an element in my Coxeter group, W. So gamma of W is a set of all V such that the set of fixed point of V contains the set of fixed point of W. Actually, this is yes, sorry?
Is this the usual parabolic subgroups we know from Coxeter's theory?
Yeah. It's the same. Mm-hmm. It's a reflection group. Okay, so and now if you the set of roots of this group is included inside the set of group of W, and the decomposition into positive and negative roots of R, it induces a decomposition of positive and negative roots in this subgroup as well. And now you can define generators and simple roots of this parabolic group. So it makes sense to look at the simple roots and the roots and the simple roots of this parabolic subgroup. So when W is a symmetric group and sigma is a permutation, then gamma of sigma is just a subgroup which preserves the cycles of sigma.
You mean preserves them as sets?
Yes, preserve them as sets, yes. That is, all the cycles are in some sense included in a cycle of sigma as subsets. Mm-hmm. Now, I need to define a notion on the set of non-crossing partition, which is the notion of Crevera's complement. If W is an element, is a non-crossing partition, then its Crevera's complement is a complement. If you want if you go for, you know that W is a node geodesic from E to C on the set of on the Kelly graph. So W minus C is the complement, is how you go from W to C inside the group W. It is called the Crevera's complement, and it turns out that it belongs also to the because it is also on a geodesic from the identity to C. It belongs also to the set of non-crossing partitions. So this map is called the Crevera's complement. You see, it satisfies some duality relation that W times K of W is equal to C, which is just this relation written in another way. And it turns out that K reverses the absolute order. That is, if V is smaller than T, if V is smaller than W, sorry, for the absolute order, then K of W is smaller than K of V for the absolute order. So it's a map which reverses the order on the set of non-crossing partitions. And now the very important fact is the following: that if V and W are non-crossing partitions, which are in cover relation, that is V is smaller than W and there is nothing between V and W, then if V is bigger than W in the Bruhat order, then K of V is bigger than K of W in the Bruhat order. That is, K preserves the Bruhat order in this case. So this is the first proposition. There is a kind of converse to this proposition, which is the following. If V and W again form a cover relation, so V is smaller than W. And now we suppose that V has full support in the set of non-crossing partitions. That is, if we look at a reduced decomposition of W, then it uses all the simple reflections. So this restriction of the set of possible V. Then the following is true: if K of V is bigger than V, than K of W in the Bruhat order, then V is bigger than W in the Bruhat order. So you see, this is the opposite implication, which is here. So these two things show that the Creveras complement, which is something which is well known in the theory of non-crossing partition, has a very deep relationship with the Bruhat order, which was something which has not been observed before, I think. And so this will be very helpful for us. And this will allow us to characterize the relation, the square relation, the order relation that I'm interested in understanding. So if V is smaller than W for the square relation, then V has to be smaller than W for the order relation, and V has to be smaller than W for the Bruhat order also. But the converse is not true, actually. It's not enough to have both these inequalities in order to have this equality. And the true necessary and sufficient condition is the following. V and W, let me assume that they are inside they are both non-crossing partitions. Then V is smaller than W in the square order, if and only if the set of generators of simple generators of gamma of V, of the parabolic subgroup of V, is included inside the simple generators of the parabolic subgroup of W. So reminder, maybe it's not a reminder, but actually this turns out to be true. V is smaller than W inside. I didn't say that, so it's not really a reminder, but it's true. V is smaller than W in the absolute order if and only if the parabolic the parabolic subgroups are included in this way. But for the absolute order, we ask a stronger relation that the simple generators are of gamma of V are included as inside the simple generator of gamma of W, which is not implied by this. Okay, so it turns out that this implies that the order ideals, all the W which are smaller than V for this order, they are all Boolean lattices. So we have seen that in the case of interval partitions, which are the case that V is equal to the Coxeter element. And then I said it is a set of interval partition. It is a Boolean lattice, but actually these orders ideals are also Boolean lattices. They correspond to these taking subsets of these sets here. There is also a characterization of the double order, which is the following. So as I said, if V is smaller than W, then for the double order, then V is smaller than W for the absolute order, and W this time is smaller than V for the Bruhat order. So we have the opposite relation now. The converse is not true. These two relations are not enough to ensure that V is smaller than W in the double order, but we have a very nice characterization. So V and W are such that V smaller than W in the absolute order, then V is smaller than W in the double order, if and only if V, considered as an element in the parabolic group here, the gamma of W, has full support. That is, any element in V, I mean, the element V can be written, I mean, any reduced decomposition of V with using simple reflection in this group contains all the simple reflections here. So, I mean, this is what it means that it has full support here. And it turns out that if we look at the order ideals, now the order ideals for the opposite orders, that we fix W and we look at all the V which are larger than W for the double order, then the image by the Creveras involution of these order ideals are the order ideals E for the square order. So they are also Boolean lattices. Okay, so we see that there are lots of Boolean lattices inside these orders. So maybe I could go back to show you on this picture. Okay, so here, for example, if you look at the interval of elements which are above this element, we see that they are obtained by they form a Boolean lattice, as you see here. Again, for this element, the elements which are larger than this element for the double order, they form a Boolean lattice, actually just a lattice with two elements in this case. Okay, and actually you can see that by using the Creveras involution, this Boolean lattice here is mapped by the Creveras involution to some. I don't remember exactly which one. I think it is this one here. We have. I think probably it is this one. I'm not completely sure. Oh, okay. I don't remember. Sorry.
For your info, I think we have like 5 minutes left.
What? I have only 5 minutes left. Okay, so okay, in 5 minutes left, I will just very quickly say that there are many connections between these objects and cluster algebras. So I don't really have time to explain details, things about that. Just one thing that you look at intervals we look at interval for the two orders, so the square order and the double order. For the square order, for example, there is a unique interval of maximal length, which is the interval between E and C. And there are two interval types of length n-1. The interval from E to the Creveras complements of reflections, and the interval which go from the simple reflections to the maximal element, the Coxeter element. And it turns out that these intervals are in bijection with the set of minus simple reflection, which is these intervals here, and the set of positive roots, which are in bijection with these elements here, which are also called the set of almost positive roots. So the almost positive roots occur very naturally in our context. And so this suggests a connection with cluster algebras. So I don't really have time to explain what is a cluster algebras. So here I just show a picture. I could show you a picture of the intervals of those. There is one interval of maximal length that you can see here, and interval of size 2, which are all the intervals from these points to the smallest element, or intervals from these 3 points to the maximal elements. Okay. So I don't really have time to explain what is a cluster complex, but the cluster complex is obtained by defining a symmetric binary relation on the set of almost positive roots that is defined here, that I don't have time to define here. And the cluster complex is just a simplified complex that is made of subsets in the set of almost positive roots, which are say equivalent classes for these binary relations. And this simplified complex, it is due also to something that maybe many of you have heard of, which is the associated, which I don't also have time to explain here. So the proposition is that the number of intervals of 8K for the square order is equal to the number of faces of cardinal n-k of the cluster complex, which is also by duality equal to the number of faces of cardinal k of the associated one. And we have a bijective proof for some Coxeter elements, which are known as bipartite Coxeter elements. Again, there is also enumeration properties of the intervals for the double relation. The number of intervals whose rank is equal to k is equal to the number of faces of cardinal k of the positive cluster complex, which is the restriction of the cluster complex to the set of positive roots. And we have again a bijection as a general case. And now, just the last 2 slides. We can also define a binary relation on the set of positive roots. What is this binary relation? This binary relation is a relation which tells you that 2 roots are in relation if and only if their product in some order is smaller than C in the absolute order. Which is essentially this relation tells you that the 2 roots are non-crossing in the sense that I used it in the beginning of my talk when I explain what are non-crossing non-crossings. What is a crossing? A crossing is a pair of roots which do not satisfy this. And we add this. I add this property here, alpha, beta. The inner product has to be negative. And let me look at the associated simplicial complex. Well, okay, so this is what I said about non-crossing relation. Okay, now this is a graph of the relation which is here on the set of roots for S3. So 1, 2, 2, 3, and 1, 3. And the graph of this relation. And now we have and this graph here is just the associated simplicial complex associated to this relation here. Okay. And this works also in the case of n equal 3. Actually, it works for n, for any Coxeter group. Here is the relation. We have a binary relation which is given by this graph here. And what you can check is quite amazingly this binary relation. If you look at the simplicial complex associated to this binary relation, you find exactly the order relation for the square order that we have here. Okay, so this is just a hint of the very, very rich relation that exists between the Coxeter groups, non-crossing partitions, and interval partitions. And maybe I will stop here. Thank you very much for listening.
Thank you.
Thank you.
This was full of very interesting things. Many of which I've heard for the first time, even the ones I think that were not supposed to be new. So, do we have any questions?
I have a small question. Right. So, thanks for beautiful talk. But this is combinatorics, really, and nice deep mathematics, finite mathematics. But you did with Nika and Goodman some approach type B freeness.
Yes, yes.
Did somebody did Boolean freeness or some other type D or some other?
Well, I mean, the result of my talk is that we can define interval partitions.
Yeah. For
type B. Okay, so because of that, we may try to do the same thing that we did with Nika and Goodman, but with Boolean cumulants. Type B Boolean should be. I have not looked at that. I think nobody has looked at that, and that's something that somebody should look at. Type B Booleans, this should exist because of just of the talks that I gave. You see, and because of the paper with Andu and Goodman. We know that there is some kind of type B probability, and they should be type B Boolean independence. But I don't know what it looks like, and someone should look at it.
Anyway, so there's some work in progress.
Yeah, sure. I don't think that anybody is looking at that presently. I don't know. I think someone should look at that.
Thank you once more, and I'll be in contact with you later. Thank you.
Sure. Certainly, Mike.
So I have a question. You, from my point of view, interval partitions are more or less the same as compositions of a number.
In some sense, yes.
In type A, at least.
Not exactly.
Why not exactly?
Because in composition, you have just numbers, not. I mean, oh yes, yes, I see what you mean.
In bijection,
yes.
Yes.
It's in bijection. Yeah, sure.
I'm pretty sure there are standard analogs of compositions in other types, because I've seen the quasi-symmetric functions in types BCD at the very least.
Yeah.
Are they still in bijection with the interval partitions that you defined in those other types?
I must admit that we gave the definition. We looked at a lot of properties of this order, square, but we didn't really look at what these interval partitions look like. I mean, they are quite easy because I gave a characterization. You just take your Coxeter element. You just take a subword of your Coxeter element. That's all. So it's very easy to look at these interval partitions. They are much easier to understand than the non-crossing partitions. But I have not tried to look at. I mean, certainly there are lots of things to be done around that have not yet been done, and that should be done, certainly. So I don't really know answer to your question.
But are they in bijection with the subsets of S again?
Interval partitions?
Yeah.
Yeah, interval partitions are, yes, they are, you can define them. If you have a subset of the simple roots, then you take the product of the simple roots in the same order as in your Coxeter element, and you get some element, some non-crossing, some interval partition. That's the definition, more or less.
Okay.
I'd like to ask you a question.
Yes, please.
Hi, Philip. So if I understood correctly, towards the end of your talk, you have those simplicial complexes. Those are actually flag simplicial complexes because you were defining them as clique complexes of graphs.
Yes.
So for those complexes, there is the notion of the gamma vector, which is conjectured to be non-negative. So have you looked at the gamma vector of that complex you had at the end?
No. I mean, certainly there are lots. I mean, I worked on this with Matthieu, and we finished about on that 1 year ago. But since then, he has done some other things. I've done some other things, and we have not come back. And certainly, there are, as I said, I hope many people will get interested and try to. There are many open questions in this, and we don't know about this gamma vector. No, but certainly, looking at the gamma vectors, one of the ways that we arrive at this connection with the cluster complex, because there are numerical connections, and we have some bijections, but still we are very far from understanding why these things are really connected. I mean, we have lots of numerical connections, but we are very far from understanding this really in a satisfying way, I think.
Okay. Thank you.
So here's perhaps a less relevant question, but where did Rota do this probability theory in terms of this set partitions? I don't think I've ever seen that. Also, I've seen a lot of sums over set partitions in Rota's work.
Rota, you mean? What Rota did is that he used the set partition and the Möbius function on set partition to define the cumulants in the classical case, in the classical probability theory. Because cumulants can be defined by looking at the logarithm of the Laplace transform of a probability distribution and the expansion of these elements. But what Rota did is that he did it in a more combinatorial way using set partitions, exactly in the way that I presented. I mean, this is the way. This is what inspired Speicher to do his.
Maybe I can make it. I mean, I'm always claiming this. I was inspired by Rota.
Yeah.
But when I tried to find in his papers really explicitly something about this, it's very hard. And maybe Terry Speed is maybe the name one should look, because he did this kind of.
Okay, so you invented also the Rota's cumulants, classical cumulants in some sense, or?
Yeah, I mean Rota has all this abstract theory, but I mean really finding a definition of classical cumulants in terms of summing over non-crossing partitions. I tried to find it just recently for a lecture, but I didn't find it. So maybe it's not there.
So how did you get this idea of your formula for moment cumulant formula. Then
I read Rota. I think in principle the background is there.
Yes.
But yeah,
yes, but
I have to say I don't really remember.
It's not
I thought I got it from Rota, but okay.
Yeah.
Perhaps I can say one thing though. The relationship between classical moments and cumulants is quite close to what in combinatorics is called as the exponential formula, or in the theory of species is that Joyal developed. So it's the same combinatorics is present there.
Yeah, I mean you find it in probability both if you, Chioyayev or Billingsley, but you have to know where to look. So, but I don't know. And then it goes back in time to the beginnings of probability theory.
Yes.
I think Rota gave somehow, there's this very formal frame of coset and multiplicative functions. I think that was what I was really motivated. Multiplicative functions.
What inspired you, yes. Yes, because
but saying that free cumulants are multiplicative functions in classical probability theory, I'm not sure whether this can be found in Rota.
Okay.
But Terry Speed, Terry Speed wrote a couple of papers on kind of cumulants, and I think this is maybe the closest.
Okay. Well, the point is that, of course, in classical probability, it's much less useful to have this combinatorial thing. It's because you have you can take the log of the Fourier transform or things like that, which are more convenient in an analytic way, and so I think it's really in non-commutative probabilities that it is very useful to have these formulas.
But if I can say, historical, I remember the old book by Kolmogorov about infinite divisibility with Gniedenko. And in that book, there is a cumulant, so they call semi-invariants in that language. Because this is logarithm of additive invariant, and there is a formula which is like cumulant moments. But not in the language like Roland present and using lattice structure, only just using Möbius function for all partition, and then, but it's not so clever, but it's, at least I first time found that in probability books, Gniedenko, Kolmogorov, infinite divisible laws, that book. But then I remember Roland Speicher when I was in Heidelberg, when he talked his result, and I think Professor Waldenfeld asked Roland, where is the Möbius function for the non-crossing? And Roland discovered this at once and was very nice. But this was 30 years ago, Roland, or maybe more, something like this.
Yeah.
Very beautiful, beautiful time in Heidelberg.
Maybe I can also ask a question concerning, so in non-commutative probability, so we have this result that, the only notions are free probability and Boolean, and maybe the classical, and okay, this corresponds somehow to the Bruhat and the total order. So the question is, is there a version of this theorem about orders of embeddings or orders in a symmetric group, such that under some natural conditions, maybe the total and the Bruhat order are the only ones?
I don't know, because there is at least another order, which is the weak. There is a strong order, but there is also the weak order, which is also very important. Which is also a lattice order on the whole symmetric group. So I would say in the case of the symmetric group, there is a third order, which is also.
But this has no probabilistic interpretation, or?
I don't know.
You get a chain, right?
That's a good. That's a good question. I don't see any. The problem is that there are two orders, one on the right and one on the left. Okay, they are equivalent, but they are not the same. So I don't know whether one could use them to do anything about probability theory. That would be that would be maybe again someone should look at that. Certainly there's some. Maybe there's nothing. But that's. Because of course you have to, in your theorem about classical about Boolean and free probability, you have to make some assumption. Of course, you can relax some of these assumptions, get monotone independence, things like that. So I don't know whether one could do the same thing with the weak order in symmetric groups. Maybe there's something.
Yeah. Or the question,
I don't know. I've never thought about that. So.
Yeah. A question would be, what are natural assumptions on orders such that maybe Total and the Bruhat are unique?
So if you just look at the permutations under C in the weak order, you get a chain. That's perhaps not very interesting in the probabilistic way.
No, of course. No, but on the other hand, the weak order, you can, the whole symmetric group is a lattice for the weak order. So maybe you should look at the whole symmetric group. So I don't know, I don't know.
And I've seen other orders on this end too. I think something called the shard intersection order. I forgot how it's defined, but it exists.
Yes. By reading, yes. Yeah, I no, but I'm not really specialist of that, so I don't. There should be some connection between this shard order and what we are doing, but I'm not so sure. This is one of the many things that somebody should look at, because there's so many connections between many things.
Okay, any further questions? Well, thanks Roland and Marek for the historical interlude.
Thank you. Thank you, Philip.
Yes, thank you.
Talk.
Yeah, thanks.
Roland, nice investigation.
Thank you very much for the comment. And I will amend my talk next time when I talk about Rota and Speicher, so that it's more correct.